For most of the 1960s, the space exploration programs of the United States and the Union of Soviet Socialist Republics were the crown jewels of their respective Cold War propaganda efforts. No one cut through the haze and the glamour better than the late President Kennedy, who on May 25, 1961, said, and I quote, "The impact of this adventure on the minds of men everywhere who are attempting to make a determination of which road they should take." Attempting to make a determination of which road they should take. President Kennedy is talking about the influence of achievement in outer space as it pertains to the leaders and peoples of non-aligned nations throughout the world. American or Soviet leadership in space and technology would, in the political calculus of the day, attract more allies and sway neutral minds, further isolating and marginalizing the other side. It is a cynical, geopolitical game, but it is one that justifies incredible fiscal expenditure and makes possible some of the greatest and most awe-inspiring explorations of the 20th century. But even in those days, there were voices, attempts by some to extend an olive branch and explore space not as competitors, but as partners. Even as far back as Eisenhower, overtures were made, both in terms of rhetoric and serious internal proposals. A letter from then-Administrator T. Keith Glennon to Ike, dated September 8, 1959, clearly states the desire to establish talks towards cooperative efforts in outer space, largely just in the field of information sharing, but nevertheless an off-ramp from the space race. This was after Sputnik, but before Gagarin. The Eisenhower administration balked at the idea of being the little spoon to the Soviets, and the American space effort, behind as it was in 1959, would remain so for several years.
In January, John Fitzgerald Kennedy was sworn in as the 35th President of the United States and began the momentous task of guiding the nation through the critical years ahead.
Jack Kennedy was more vocal for the idea of cooperation in space. While on a policy level, he, more than anyone else, galvanized the American space effort in the competitive lens. He also privately chafed against the budget requirements of Project Apollo and tried several times to look for a way out. Kennedy and Khrushchev meet in Vienna on June 4, 1961, to iron out large outstanding issues between the two superpowers. The meeting is tense and unproductive. He is, by all accounts, bullied and harangued by Khrushchev on issues such as the Bay of Pigs, the divided city of Berlin, and violence in Southeast Asia. Kennedy does not back down on America's overseas security interests. He does, however, suggest to Khrushchev that the United States and the USSR, quote, "go to the moon together." Khrushchev rebuffs him, determining that the military implications of large rocket boosters would deem the effort impractical. The years ahead would be hard going. In October 1961, the Soviet Union unilaterally violates a 10-year moratorium on nuclear weapons testing by detonating the largest nuclear weapon ever created. And in response, American testing resumes. The Soviet premier was testing the new president's mettle. In 1962, progress was made as both leaders, through written letters, acquiesced to cooperation in weather satellites and tracking services. Deputy NASA Administrator Hugh Dryden and his Soviet counterpart, Anatoly Blagorovov, held meetings in New York in March. Later meetings in Geneva led to agreements for cooperative research in the field of unmanned robotic spacecraft. A memorandum of understanding followed in Rome on March 20, 1963. Kennedy then took his wishes to the United Nations. In his address before the 18th General Assembly on September 20, 1963, he lays it all out on the line.
I believe, therefore, that the Soviet Union and the United States, together with their allies, can achieve further agreements. In the field of space, there is room for new cooperation, for further joint efforts in the regulation, and exploration of space. I include among these possibilities a joint expedition to the moon. Why, therefore, should man's first flight to the moon be a matter of national competition? Why should the United States and the Soviet Union, in preparing for such expeditions, become involved in immense duplications of research, construction, and expenditure? Surely we should explore whether the scientists and astronauts of our two countries, indeed of all the world, cannot work together in the conquest of space, sending someday in this decade to the moon, not the representatives of a single nation, but the representatives of all of our countries.
It is hard to ultimately judge whether these are the true hopes of a leader trapped in a commitment with an uncertain outcome or even possibility, or if they are the mere suggestion of a backup plan. One thing it clearly isn't is virtue signaling. NASA, the State Department, and the White House all circulate a triangular trade of internal memoranda in 1963, discussing how to follow up should the Soviet Union accept, including the possibility of a private bilateral approach. For their part, the Soviets, in those early days where they were very clearly ahead, wanted to kick the football of space cooperation beyond crude lunar landings. The Kennedy administration creates National Security Action Memorandum, or NSAM, number 271, dated November 12, 1963, calling on NASA to assume responsibility for developing a program for further cooperation with the Soviet Union in space exploration, a real proposal beyond vague platitudes. A report by James Webb was to be submitted in January 1964. Just 11 days later, however, American history took a turn.
Here is a special bulletin from Dallas, Texas. 3 shots were fired at President Kennedy's motorcade today in downtown Dallas, Texas. The president now making a 2-day speaking tour of Texas. We're going to stand by for more details on the incident in Dallas. Stay tuned to your ABC station for further details.
President Lyndon Johnson oversees existing diplomatic overtures already set in motion during the Kennedy era, but he lets them quietly die as American prestige and achievement grows to surpass Soviet triumph in crewed spaceflight during Project Gemini. The United Nations, for its part, was primarily concerned with arms control and the prohibition of the use of outer space as a staging area for orbital nuclear weapons. This fear leads to the Treaty on Principles governing the activities of states in the exploration and use of outer space, including the moon and other celestial bodies, or more simply, the Outer Space Treaty of 1967, which goes a long way to establish the legal framework in which countries can explore and use space. The United States, the Soviet Union, and its successor state, the Russian Federation, and the People's Republic of China are all signatories to this treaty. It leads, in 1968, to further treaties obligating nations to assist in astronaut rescue should the capability exist and the need arise. The Outer Space Treaty is perhaps the crowning achievement of the Johnson administration in the field of space cooperation. But beyond information sharing between robotic missions, such as Venera 4 and Mariner 5, and the occasional Earth weather satellite, there is no concrete cooperative effort that materializes during this period. Even the 1967 treaty's roots predate Johnson, largely based on a 1963 declaration of legal principles governing the activities of states in the use of outer space. Both sides seem to have hit a hard ceiling on working together. Locked in a stalemate, it would take a truly Machiavellian push to somehow break this mold. Enter from stage right, Richard Nixon and Henry Kissinger.
American youth today has its fringes, but that's part of the greatness of our country. I have great faith in American youth. The youth of today can change the world. And if they understand that, I think that we're going to go forward to a great age, not just for Americans, but for peace and progress for all the people in the world.
Richard Milhous Nixon, commander in the Naval Reserve during World War II, lawyer, former representative, former senator, former vice president under two-term President Dwight D. Eisenhower, has just pulled off the impossible. After losing a presidential bid in 1960 to JFK and a failed 1962 run for governor of California, Nixon is back, returned from the political wilderness, and promises to bring with him a new look on American foreign policy. Nixon takes office on January 20th, 1969, and establishes a Space Task Group designed to look ahead after Apollo and chart the future of American spaceflight. While campaigning for office, the Republican had complained about the relative lack of emphasis on science in the U.S. space program, citing what he termed a research gap when contrasted with Soviet space efforts. Robotic interplanetary spaceflight, cheaper than establishing a permanent foothold on the moon, and framed as a more purely scientific endeavor, is highly attractive to the new president. NASA has plans. Lots of them. Moon bases, nuclear engines, sending astronauts to fly around Venus, and crewed landings on Mars by the early 1980s are just a few of the fantastical post-Apollo concepts that are floating around and waiting for political sponsorship and the money that follows. But the successful conclusion of Apollo 11 and the establishment of an American space achievement that will not be surpassed dampens those wins considerably. Vietnam, the war on drugs, and the oil crisis bring back into sharp focus problems right here on Earth, and Nixon is looking to make his mark in world history through diplomacy and statecraft. Space exploration is not his first love. NASA must learn to adapt to this new reality. July of 1969 sees the publishing of a report titled America's Next Decade in Space. In it, NASA proposes a 12-person Earth-orbiting space station by 1975, followed by an even larger outpost capable of housing up to 100 people at a time, with a winged shuttle vehicle capable of routine spaceflight. While Nixon publicly supports a strong human spaceflight program and enjoys the positive press associated with it, he chooses not to act on the recommendations of the Space Task Group. Under his tenure, 3 final Apollo landings, 18, 19, and 20, are all canceled. 20's Saturn V is repurposed to launch SA-212's S-4B stage, a so-called dry workshop, a space station known as Skylab, meant to be just the start of a much larger set of ideas known as Apollo applications, an experimental foothold into living and working in space using leftover hardware meant to explore the moon. But Skylab ultimately will be the only concrete thing to result from AAP. The space shuttle is ultimately approved and funded by 1972, but not the expanded space station it was designed to service. The massive Saturn V moon rocket, which could carry 140 metric tons to low Earth orbit, was now a finite resource. No further orders are placed by NASA after 1968 beyond the original 15. For a time, in 1971, Nixon even considers axing 2 further moon landings, Apollo 16 and Apollo 17, but ultimately he relents and lets them fly. During the 4-year period of Apollo lunar missions, token steps are taken that begin, at least from a public relations perspective, to thaw the ice between the two superpowers in outer space. Astronaut Frank Borman, commander of Apollo 8, undertakes a goodwill tour of Soviet space facilities in 1969 as Nixon's representative. NASA Administrator Thomas O. Paine writes to the Soviet President of the Academy of Sciences and broaches the idea of cooperative space ventures. Under Nixon's urging, he continues to suggest ideas along these lines, including proposing that a Soviet spacecraft dock with Skylab. Khrushchev was long gone. He had been ousted from Soviet leadership in 1964. In October of 1970, 5 NASA representatives fly to Moscow under Soviet invitation for talks on providing compatibility to the rendezvous and docking systems of the next generation manned spacecraft and space stations. American and Soviet docking systems engineers, such as Vladimir Siromyatnikov and Caldwell Johnson, hammer out ideas to make possible cooperation in space in the 1980s and beyond. Nobody is going into these meetings with the idea of an immediate short-term cooperative mission, but as is increasingly the case, political winds carry the day. Secretary of State Henry Kissinger instructs acting NASA Administrator George Low in 1971 to use informal back-channel conversations to push for the possibility of an early U.S.-Soviet docking mission. Upon his return, Low reports that the Soviets seemed receptive to the idea. This leads, finally, to firm commitments in 1972, signed by President Richard Nixon and Soviet Chairman Alexei Kosygin on May 24th, outlining an official U.S.-USSR agreement concerning cooperation in the exploration of outer space, which among other things commits both nations to the exchange of lunar samples taken on Apollo and Luna missions, the exchange of weather data and detailed medical information from the respective space programs, and outlines a joint test mission to develop compatible rendezvous and docking techniques. This is a hallmark to the Nixon-Kissinger approach to diplomacy. To strip away the fluff and put it all into brass tacks, they are attempting to drive a wedge right into the heart of the communist bloc by separating the Soviet Union and its satellite states from the People's Republic of China, who, while nominally subscribe to a similar subset of ideologies and opposition to what they view as American capitalist imperialism, nevertheless have soured considerably on their Soviet former comrades over a building litany of frustrations that have gone on unaddressed. The aging Mao Zedong sees himself, not the Soviets, as the true elder statesman of communism, and as the ideological successor to Joseph Stalin. And Nixon is the first American president to recognize this and feed his ego. Nixon pursues a new policy towards embracing communist China, which isolates the Soviets and puts immense pressure on them and their new leadership to come to the table on a number of issues. This, in a nutshell, is Nixon's triangular diplomacy, a tenuous balance of power that, in his view, may secure the peace into the next century. Nixon's pursuit of bilateral, pragmatic relations with both the USSR and China makes possible a new chapter in the Cold War known as Detente, the Forgotten Peace. It leads to the first major conferences on nuclear arms control, known as the Strategic Arms Limitation Talks, or SALT, which leads to the first ever nuclear arms control treaties between the two superpowers. And, getting back to human spaceflight, the strategy of Detente makes politically possible for the first time a joint U.S.-Soviet mission. And for the first time, it affords Americans involved in the space program the opportunity for something they never expected. A look, highly controlled and curated as it was, into the competition behind the Iron Curtain. By 1965, the Voskhod line, An improved Mark II of the Vostok that had first sent mankind into orbit of the Earth had run its course. Its greatest headline achievement was Voskhod 2 and history's first spacewalk by cosmonaut Alexei Leonov in March of 1965. Unlike the Americans with Project Gemini, the Soviets did not see Voskhod as a stepping stone. Rather, for them it was a stopgap because the real future of Soviet spaceflight was a vehicle called Soyuz. Voskhod only flies 2 crewed missions into space, the spacewalk milestone previously mentioned, and a record 3-person crew before that. But after these 2 flights, the entire program is canned, with the new Soviet leadership less focused on prestige and milestone missions. All efforts are put towards developing Soyuz and a Soviet lunar architecture ahead of the American Apollo effort. It is here, under leaders Leonid Brezhnev and Alexei Kosygin, that the pillar of Soviet space ambition begins to collapse under the weight of its own shortcomings. A 1-2 punch cripples Soviet progress. First, the death of chief designer and rocket pioneer Sergei Korolev in January 1966. And second, the fatal failure of the first crewed Soyuz flight, Soyuz 1, which ended in the death of the sole occupant, Vladimir Komarov, in April of 1967, when his parachute failed to open after re-entry. This is a traumatic blow from which the Soviets never really recover. But these events are merely the most visible symptoms, they are not the cause. The Soviet Union's economy is roughly half the size of that of the United States, and while their centralized state socialist approach granted them greater control over their own spending, the Soviet space effort is fragmented and inefficient. It has a higher labor footprint than the American effort, despite commanding consistently smaller budgets. It is estimated that the Soviet lunar effort cost somewhere in the neighborhood of $12 to $13.5 billion compared to the $30 billion spent by the United States to reach the moon before the end of the 1960s. Another key difference in why the Soviet effort was unsuccessful is not without a tinge of irony. It is the American NASA that runs a much more centralized, top-down organizational structure to minimize duplicated efforts across industry, whereas the Soviet approach is much more decentralized, with competing design bureaus and clashing personalities sucking wind out of the broader effort. It's not just the space program that languishes under Brezhnev. Even in the broader view of Soviet culture and history, his tenure over the country comes to be known as the stagnation era. The Soviet space program is merely the lightning rod for that image. It took until October 1968 for the Soviets to recertify Soyuz and fly into space again with a crew. Somewhat ironic, again, the very same month Apollo-7 redeemed the American effort set back by the fire of Apollo-1. Soyuz 3 returned cosmonauts to flight, though its attempted docking with the uncrewed Soyuz 2 failed. Meanwhile, the Soviets were developing both the N-1 moon rocket and LK lunar lander, as well as the Zond circumlunar program, and the successful mission of Zond 5 that September seemed to point in a good direction. In January 1969, Soyuz 4 and Soyuz 5 successfully docked with each other, and the cosmonauts transferred by spacewalk between the two vehicles. That was a critical accomplishment, because unlike the American Apollo spacecraft, the Soviet docking system designed for the lunar program did not allow for intravehicular transfers. There was no pressurized access between the two vehicles. A crew of only 2 would fly into lunar orbit, and then one single cosmonaut would have to spacewalk down the sides of the vehicle stack and enter the lunar lander from the outside. Follow-on missions, Soyuz 6, 7, and 8, did not achieve their respective objectives, and the program continued to stumble. Soyuz 9 sets a new spaceflight endurance record, spending 17 days, 16 hours, and 59 minutes in orbit. The Soyuz is smaller than Apollo and much less capable in terms of maneuvering, but does offer its occupants a far greater degree of soft comfort in things such as living space and amenities. Soyuz crews have an early version of a working space toilet, and more habitable volume as compared to the Apollo. The interior of the Soyuz is split into two parts: the descent module, in which the cosmonauts fly the spacecraft, and the orbital module, in which the cosmonauts live. This two-room setup is extremely comfortable by the standards of the 1960s and 1970s, and allows for a combined total internal volume of up to 370 cubic feet for certain variants, compared to just 210 cubic feet for the unified, singular living and working space of the Apollo command module. Speaking of variants, of the Soyuz there were many. Different docking systems, different orbital modules, even ones with spy cameras. For a vehicle originally designed to fly to the moon and having failed to do so, it performs exceptionally well in low Earth orbit. Its legacy is look at how long it has lasted. Still today, the Russian Federation flies newer generation Soyuz vehicles to the International Space Station, and their unmanned derivatives, the Progress, for in-space resupply. The Chinese have adapted the design for their own purposes, with the Shenzhou vehicle. But in the early 1970s, all of that is history yet unwritten. The N-1 moon rocket, upon which the entire Soviet manned lunar effort is staked, is a dismal failure. It launches 4 times between 1969 and 1972, and fails spectacularly each time. The violence of its explosions wreak havoc on Soviet launch facilities, with a July 3, 1969 attempt causing an incredibly long delay. The rocket program will ultimately be canceled in 1974. Unmanned Luna missions, launched on the workhorse Proton rocket, would be the pinnacle of Soviet flights to the lunar surface, achieving robotic sample return and autonomous lunar rovers. In 1971, while the United States is still sending manned missions to the moon, a Proton rocket launches Salyut 1, the world's first space station. The idea of a space station had been around since the start of the space age, a large vehicle in orbit of the Earth on which new pieces could be added, and crews could be ferried to and from the Earth with smaller vehicles. Both the United States and the Soviet Union planned to have space stations from the very beginning, but the moon race got in the way. The Americans were first to abandon their plans for a military space station, the Manned Orbiting Laboratory, in June 1969. This would have been a classified program run entirely by the U.S. Air Force, but Soviet planning along similar lines persisted. A military and reconnaissance platform known as Almaz, begun under Khrushchev, was one of the few programs carried over under Brezhnev. In 1969, however, the Soviets began their pivot away from lunar ambitions and began working on a series of civilian scientific space station missions known as Salyut. The military Almaz and the civilian Salyut come from competing design bureaus within the Soviet space industry, but their similar size and form factor gives the Soviets the perfect cover story. Almaz military missions, like jokers in a card deck, will be shuffled into the Salyut program under the guise of non-military civilian spaceflight. The early Salyut and Almaz stations were fairly simple and consisted of only 1 or 2 pieces, and in many cases were only visited by 1 or 2 flights each before being deorbited. Salyut 1 launches in April 1971 and is visited by Soyuz 10, which manages a partial docking but fails to establish a firm link-up and aborts its mission entirely, the crew never having entered the station. This is followed by Soyuz 11, which does successfully dock to the station and spends 23 days aboard. But a valve failure in their Soyuz before re-entry depressurizes the vehicle before the crew has a chance to don their spacesuits, killing all 3 cosmonauts before landing. Of the 16 individual cosmonauts launched on Soyuz between 1967 and 1971, 1/4 lost their lives. Of the over 30 Soyuz-derived spacecraft launched in the same period, all but 9 experienced considerably significant failures. The Soviets, undeterred, press on. A second Salyut is lost in a launch failure in 1972, followed by an Almaz failure in 1973. A third attempt again fails. During this time, the American Skylab program manages to demolish the spaceflight endurance record, with 3 onboard missions of 1, 2, and 3 months duration, respectively. But the Soviets, hard-charging as ever, do not give up. A second Almaz mission, given the cover identity of Salyut 3, is launched in 1974. Being a military space station, it serves as an orbital testbed for a variety of military technologies, including a 23mm onboard autocannon, which makes Salyut 3 the first armed spacecraft in history, and a blatant militarization of space hardware. It is, according to Soviet thinking, a defensive close-in weapon system meant to provide an answer to American aircraft-launched anti-satellite missile technology, which by that point was almost 15 years old. It is in this context of a renewed Salyut push and an endless future for Soyuz that the Soviets are approached by the Americans for a joint mission sooner rather than later. For their part, the United States is in dire budgetary straits and running out of usable hardware. The Apollo Applications Project in its inception assumed an incredible surplus of usable launch vehicles and spacecraft. 25 Saturn 1Bs in May of 1967 dropped to just 3 2 years later. After the moon missions, there just simply weren't going to be enough Apollo spacecraft left to fly missions with. Ultimately, only 2 complete Saturn 1B launch vehicles were built and never flown. SA-209, converted into a possible rescue vehicle for Skylab 3, and SA-211. First stages were built for SA-213 and 214, but the program was axed before the completion of their S-4B upper stages. The near-term mission concept, while technically feasible, would undergo a headache-inducing give and take. A Soyuz Skylab mission is considered and scrapped, as is an Apollo Salyut flight. Neither side wanted to modify their existing space station hardware, and NASA wanted to protect shuttle development funding, and wasn't going to put another single cent into the Skylab program, which by 1973 was set firmly in stone. They would need to pull off this flight with existing spacecraft and with minimal changes. This would very much be a mission plucked out of the tail end of the Apollo stockpile. The launch vehicle, a Saturn 1B known as SA-210, had its 2 stages built in 1967 and then was placed in long-term storage because of a lack of an immediately available mission at the time. A backup launch vehicle, SA-209, is available on standby as well. Never used, it is currently on display in the Rocket Garden at the Kennedy Space Center Visitor Complex. The spacecraft itself, CSM-111, was finished in March of 1970 and then put into storage until July of 1972, approximately 2 months after the firm political commitment that was made to a joint mission with the Soviets. For the next 2 years, until August 1974, ASTP-specific modifications would be made, taking lessons from both the lunar missions and the 3 Skylab flights. ASTP, the Apollo-Soyuz Test Project. Funding, at least in the early days, came out of the Skylab program, some $45 million in 1972 and 1973. That's some $355 million in today's money, on a mission that used existing hardware. Only one other Apollo Command and Service Module, CSM-119, the aforementioned Skylab rescue vehicle, was built but never flown. CSM-115 was partially completed, but never fully flight-ready. The big problem with Apollo-Soyuz is simply how to dock two vehicles that were never designed to be compatible, not just technically, but politically as well. Both Apollo and Soyuz in this era utilize a male-female docking port design. In the context of a rendezvous and docking mission, one vehicle with a drogue acts as a stationary, passive target, while the other, with an imposing spike known as a probe, serves as the active vehicle. Male active, female passive. Boys will be boys. But when it comes to international cooperation, particularly when both sides don't particularly like or trust each other, and neither one can afford to lose face, neither the Americans nor the Soviets want their vehicle to be the passive one. Both sides are pushing for their own spacecraft to be the active partner, and joint conferences begin to get heated as mission planners butt heads. There is another issue at play as well. The Apollo spacecraft maintains an internal environment of pure oxygen at 1/3 sea level pressure, approximately 5 psi. The Soyuz, however, operates a nitrox mixture at a much higher pressure, more closely approximating the atmospheric conditions on the surface of the Earth. Bringing these two vehicles together, even if you could solve the docking port issue, would create its own problems, since they have dissimilar internal atmospheres. The solution was to create a space between the two vehicles that could serve as an airlock and a universal docking assembly. Inserting a third piece between the Soyuz and the Apollo solves many of the issues mentioned. The two spacecraft cannot literally be opened to each other. There would need to be a buffer zone, a no man's land, an international checkpoint into which astronauts or cosmonauts could enter and then seal off their own vehicle before opening a doorway to the other side. So in terms of specialized, bespoke hardware that would need to be designed and fabricated in order to make this mission possible, a specific docking module that could act as an adapter and buffer would need to be built and launched, as well as a completely new kind of docking port that would allow both vehicles to serve as either the active or the passive partner in space. Unrelated to the joint mission with the Soviets, at least on the American side, were studies in 1970 by engineers at the Spacecraft Design Division in the Johnson Space Center, given a free license during the peak of American crewed space exploration to explore what future designs might be, and the evolution of crewed spacecraft technology. Looking ahead at the time to what came to be Skylab, senior engineer Caldwell Johnson, responsible for many aspects of the Mercury and Apollo spacecraft, and a team working under him explored the concept of a so-called androgynous docking port that, unlike the male-female design, had no hardware obstructing the passageway between the two vehicles that would need to be removed. It was an improvement from both a standpoint of design and engineering elegance, but also for procedural and planning purposes. The problem with male-female docking ports is that because they are purpose-built to interact with each other, there's no compatibility with just one half of the two-part system. In other words, two male spacecraft would be unable to dock with each other, as would two female spacecraft. Switching to an androgynous, universal design would, in effect, be the implementation of an industry standard, making all vehicles that carried the system capable of docking with each other. It's something that, particularly with the coming age of the shuttle, NASA believes is a crucial improvement. Unfortunately, there is not enough money to develop this system in time for Skylab. But it is an ace up NASA's sleeve when Johnson, along with his boss, Robert Gilruth, and other senior NASA leadership, meet with the Soviets. Soviet engineers are thinking along similar lines. The androgynous system not only makes it so that either spacecraft, Soyuz or Apollo, can fly as the active rendezvous partner, but it also removes any potential loss of face for either nation to have to fly a receptive, so-called female spacecraft. The designs were co-equal and neutral, just as the political leaders wanted it. But now it was time to transform lofty political ideals and platitudes into concrete engineering solutions, because this was now real, and the laws of physics cannot be fooled by speeches. Leading the American side of the engineering and operational aspects of the joint mission was Flight Director Glynn Lunney, named Technical Director of the ASTP project. His counterpart on the Soviet side was Konstantin Bushiev, a senior engineer at the Central Design Bureau of Experimental Machine Building, the organization that built the Soyuz. Both men were responsible for hashing out the details of turning a political gesture into a real mission. ASTP is, for this reason, extremely unique in the history of both nations' space programs. Typically what happens is that agencies like NASA bring ideas and concepts forward to political leaders, who then, working within the constraints of budget and political capital, chart a course forward for the space program and country. This mission was the opposite. It was a political directive that was imposed upon the agency. No one at NASA was scrambling for a joint mission with the Soviets, and it's safe to say the same was true for the other side. For that reason, it is a challenge unique in NASA's history, and it is received by some like an unwanted homework assignment. It would largely fall on the two personalities of Glynn Lunney and Konstantin Bushiev to make it work.
Human relations is tougher than solving technical problems. We'll probably eventually send people to other star systems someday. Well, that's a very difficult job, but that's probably an easier job than making everything roses between countries on Earth.
The hypothesized American androgynous docking port is hydraulically activated and uses 4 large guides, also called fingers, which, when roll-oriented with an identical system, allows for a series of latches to engage and connect the two spacecraft. The latches are set around a ring, which can be hydraulically extended and retracted, and this hydraulic buffer absorbs the excess kinetic energy of the vehicles immediately after contact and capture. The Soviet design is on paper highly similar, but instead of being hydraulically actuated, it is mechanical, driven by rods and gear teeth, and uses 3 fingers instead of 4. Minor differences like this, and the refusal of junior engineers to compromise or change, threaten to blow up the entire project.
Back then, we didn't understand much about the Russians' technical capability, and what we found out was that they had very reliable spacecraft that could do the job that they were built to do. We had more advanced technology. Some examples: we had a computer at that time in the spacecraft, and they didn't in theirs. They had what we called a jukebox. It was an electromechanical cylinder that had a rotating drum inside, and so they could move that cylinder drum inside the cylinder so that a column came up. On the drum were all of these commands, and you could finally get to the right one by rotating the drum, then going up a column and finding, well, here's a switch to turn on a light, or here's another switch that activates the reentry program, something like that. So we were doing all of that on a computer at the time.
The three-fingered mechanical design is the brainchild of Vladimir Syromatnikov. Eventually, on this point, a compromise is reached. The Americans concede and will adopt the Russian three-fingered design, but will maintain the hydraulic components of their androgynous port. This system, developed for ASTP from a primarily Russian design, becomes known as the Androgynous Peripheral Assembly System 1975, or APAS-75 for short. There are significant differences between the hydraulic American end and the mechanical Soviet end, but they are compatible with each other, and both can serve as either an active or a passive partner in a rendezvous mission. One hurdle cleared. Other American concessions include adding new constraints to the operation of the Apollo spacecraft while it is docked to the Soyuz, including turning off 2 of its RCS quads, ensuring no roll maneuvers are made with more than 2 of its 4 thruster banks, to prevent excessive structural loads on the Soyuz spacecraft. At least, that's stated as a concession. The reality is, 2-jet roll is already standard operating procedure in most cases on Apollo. The Soviets are forced to make concessions of their own. They would agree to reduce the operating cabin pressure of the Soyuz spacecraft nitrox atmosphere from 14.7 psi to 10, reducing the amount of time required for docking module pressurization and crew pre-breathing. They also accepted American flammability and safety rules inside their own spacecraft, not normally part of the Soyuz operating procedures, accepting American-supplied fire-resistant material for cosmonaut clothing and storing their onboard equipment in American-supplied fireproof containers.
So this airlock, called the docking module, was an adapter or a tube between our spacecraft that actually we could change the pressure in it to make a transfer. It's sort of like escaping from a submarine. You know, they have airlocks for that. Well, we had the same airlock concept between our spacecraft because they had different pressures, air pressures.
They also begrudgingly accepted the presence of U.S. personnel at the Soviet launch site, participating in pre-flight final checkout of the flight hardware, as well as Americans present inside the Soviet control center, an uncomfortable proximity to many in the Soviet bureaucracy. Perhaps the biggest concession of all was that the Soyuz, for the initial part of the mission up to and including the first rendezvous and docking, would serve as the passive rendezvous partner. The Soviets aren't necessarily being cagey because they're afraid of their own technology being stolen. They're worried about losing face when confronted with the shortcomings of their hardware. The Apollo and its Saturn 1B vehicle is, quite frankly, the more capable spacecraft of the two. It is the only rocket capable of lifting the docking module and the Apollo spacecraft together in a single launch, with sufficient payload margin and volume in the same space that a LEM would be stored in on a lunar mission. Apollo is doing the heavy lifting on this flight. The Soyuz rocket is unable to launch both a Soyuz and a docking module together. The Soviets are also fairly limited by the capabilities of their launch vehicle. Normally, an Apollo spacecraft on a low Earth orbit mission, such as on Apollo 7 or Skylab, enters an initial orbit altitude of around 100 nautical miles, or 185 kilometers above the Earth. But in order for Apollo to serve as the active rendezvous vehicle, it must enter a lower and therefore faster orbit of the Earth than the Soyuz, with which it must catch up to after launch. The Soviets are incapable of launching Soyuz any higher than 190 nautical miles with their launch vehicle. There needs to be a sufficiently wide gap in the altitudes for one spacecraft to catch up with another in a reasonably short time frame. The Soviets do not want to admit that their hardware is the limiting factor. They spin their wheels and things come to a head when Christopher C. Kraft Jr., during a pre-flight planning meeting, blows up and accuses them of having an impotent space vehicle.
One thing that's hard to realize now, 25 years after Apollo-Soyuz, is what the climate was like back then. And in a way, after the Stalin years and the Khrushchev years and all, Khrushchev pounding his the lectern with his shoe and all that sort of thing, why Soviets were very foreign to us, you know. After some of the things that happened, why we thought they were pretty aggressive people, and I won't say monsters, but they probably thought we were monsters, and so we very quickly broke through that, because when you deal with people that are in the same line of work as you are, why, and you're around them for a short time, why, you discover that, well, they're human beings. And in retrospect, I would say the biggest difference between the cosmonauts and us was, well, aside from their technical approach and all to spaceflight, was their history and their traditions. They were probably a more secretive society, partly because their population had been overrun by invasions for 1,000 years. And you know, in this country, we don't have that experience or that burden, so we're a much more, tend to be much more open as people. Well, when we got with the Soviets, they had their security monitors, and you could see that it was a less trusting, more closed society. But on the other hand, as human beings, why, that opened up more and more, I thought, in our relationships. And we actually came to have a very close relationship with the Soviet crew.
There are also wild tales of Soviet security during meetings, including an incident when Robert Overmyer, American astronaut, apparently moved his chair during a conference in Russia and tore loose a hidden microphone. For Apollo-Soyuz, the American spacecraft will enter an excruciatingly low 83 nautical mile orbit of the Earth, just 154 kilometers. Scraping the top of our planet's atmosphere, it will require an ascent trajectory considerably more depressed than ever attempted before, and American planners are very worried that increased atmospheric heating might damage the spacecraft. Additional cork-based insulation is installed on the boost protective cover of the launch escape tower, and other hardware changes are made to ensure a reasonable modicum of safety. There is considerable worry on the American side about the orbital lifetime in the early phase of the flight. The Saturn 1B launch vehicle is being pushed to the very edge to support this mission. Margins on this rocket are already pitifully small, with it necessary to load the Apollo spacecraft with only 20% of the fuel it normally carries for a lunar mission, and one whole set of internal propellant tanks removed from its service module. But now it has to also lift a 4,500-pound, or just over 2 metric ton docking module as well. This, combined with the high orbital inclination for the Soyuz Rendezvous, means the Saturn 1B vehicle is being challenged, though not necessarily pushed to its limits. That honor falls to the Skylab flights, whose spacecraft masses were clocked at around 21 metric tons, compared to ASTP's combined total of 16.8. This is still 2.5 times heavier than the Soyuz. The final 4 Saturn 1Bs, Skylab 2 and onward, have up-rated first-stage engines with higher performance. On ASTP, there is a 500-pound margin of propellant in the booster rocket for the launch window, which ranges, depending on the day, from 5 to 8 minutes tops. If they miss a launch on the first day and have to scrub, they can try again each day for 4 more days, a total of 5 launch opportunities once the Soyuz is in orbit. There is an additional 315 pounds of payload margin in the launch vehicle to account for things like small leaks or performance hits. This is razor thin compared to the margins typically available on the Saturn V. On January 30th, 1973, NASA formally announces the crew of the joint mission with the Soviets. Commanding is 3-time spaceflight veteran Thomas P. Stafford, veteran of Gemini 6, Gemini 9, and Apollo 10. The command module pilot is Vance Brand, member of Astronaut Group 5, with notable contributions of his own in mission control during the Apollo lunar missions, but he has never flown into space.
I decided that I was interested enough that I attended some of the banquets that the Soviet cosmonauts were attending here. And on my own, I went off and took Russian lessons. I paid for my own Russian lessons on Saturdays and got into their language and their culture a little bit. Finally, before the end of Skylab, sometime in 1973, as I recall, I was assigned to the mission. Tom Stafford had been assigned some time, and he had been working in the Soviet Union doing advanced planning and that sort of thing. So when we were assigned, of course I was elated. This was my first mission, and we set about to get ready for it.
The third man aboard Apollo is someone nobody expected to ever be able to fly. After over a decade of dieting and severely cutting back his alcohol consumption, Deke Slayton, Mercury astronaut, director of flight crew operations, and World War II veteran, has overcome his idiopathic atrial fibrillation. This heart condition, which grounded him in 1962, just before his scheduled Mercury flight, Delta 7, has left Deke without a single spaceflight to his name for over a decade and a half. But on March 13th, 1972, it is publicly announced that Deke is healthy and cleared for flight status. Overnight, he becomes NASA's oldest eligible astronaut and is assigned a seat on ASTP. He will be 51 years young when the mission begins and is at the time the oldest person to ever fly into space. Nobody can say Deke hasn't earned this one, but while he's a fine pilot, he has been out of the training loop for a very long time. The spacecraft he originally trained for has been gone for over a decade, and Apollo is a much more complicated beast. It falls to astronaut John Young to oversee Deke's redevelopment.
Tom and Deke, they had been my bosses. Deke stepped out of management position, being the guy in charge of all of the astronauts and the supporting facilities like trainers and so forth. He stepped out of that job to become a crewman, really anxious to fly in space. Tom, at that time a brigadier general, had worked as Deke's deputy, and I knew them as bosses, and so as we got into training, why, pretty soon I knew them more as fellow crewmen and friends. As you say, the more you get into training and everything, the more you bond. And of course we started out in systems training, and I was very familiar with the Apollo system, so and as was Tom. Deke had a little more work to do on that.
The division of labor is assigned, and work begins in earnest to bring hardware out of storage and to begin production of new hardware necessary for the flight. Rockwell is the American contractor given responsibility for the manufacture of the aluminum docking module, and they build two, a prime unit and a flight spare. It is essentially a large cylinder with rectangular protrusions just over 3 meters, or 10 feet long, and 1.4 meters, or 4.5 feet wide. This creates a free internal volume of approximately 124 cubic feet. Much of the functional hardware is mounted externally. Large spherical gas tanks for oxygen and nitrogen, and VHF-FM antennas. The pressure vessels for flight are wrapped in an external insulation cover held off the structure by a framework. Because it will ride in the internal space of the adapter panels between the Apollo and the Saturn launch vehicle, it does not have to be aerodynamically clean. It is compact and functional. One end has the same kind of drogue used on the lunar module, so the Apollo can dock. The other end, an APAS-75, enabling it to capture Soyuz. While the Americans are given the task of manufacturing the docking module, the Soviets agree to flex their manufacturing prowess on uncrewed flight tests. As mentioned before, the hardware situation for the Americans is bleak. The issue is spacecraft. They have plenty of launch vehicles. Rockets are not the problem. There's even 2 fully functional Saturn V's left over from the neutered Moon program, and a flight-ready Skylab backup, Orbital Workshop 2, also known as Skylab B, which will tragically never be used, despite considerable interest in flying it on a joint mission with the Soviets if they were willing to cut loose a Salyut for the project, in something of an extended 90-day joint flight with Skylab, Salyut, Soyuz, and Apollo. A kind of ISS 20 years before ISS. But Salyut's military connotations mean the Soviets aren't going to let the Americans anywhere near that project. And for the US, there are literally only 2 functional spacecraft left after 1973, and NASA cannot afford to fly both of them. Skylab B, had it been launched in 1975, could have survived in orbit until at least 1982, long enough for the shuttle to have come online. But NASA did not have a crystal ball, and from where they sat in 1975, they assumed 2 things that turned out to be false. 1, they assumed the original Skylab, still then in orbit, would survive until the mid-1980s. Higher than expected drag due to solar activity would bring it down in 1979. The second assumption is that the space shuttle would be ready to fly in just a couple years, probably no later than 1978. It would not actually fly until 1981. Those 2 Saturn V's will never be used, and Skylab B is now on display at the Smithsonian in Washington, D.C. On the other end, the Soviet reality is completely different. They build no fewer than 6 specialized Soyuz vehicles to test ASTP-related hardware. The variant of the Soyuz developed for this purpose is called the 7K-TM. 7 denotes the internal project number assigned by the OKB-1 Design Bureau for the baseline Soyuz vehicle in general. K stands for Korabl, which translates to ship or vehicle. The T stands for transport, and the M stands for modified. The Soviet crew is announced in May of 1973. Spaceflight Titan Alexei Leonov, the first man to ever walk in space aboard Voskhod 2, and his partner, cosmonaut Valery Kubasov, veteran of Soyuz 6. These 2 are perhaps the luckiest cosmonauts on the face of the Earth. By all accounts, they should be dead. Leonov and Kubasov were originally slated to fly the doomed mission of Soyuz 11, but were knocked off at the last minute due to an exposure to tuberculosis. Now, they are Soviet ambassadors on an international space mission of goodwill. On April 3, 1974, Cosmos 638 launches uncrewed, carrying an APAS-75 androgynous docking system aboard, testing the modified environmental control procedures planned for ASTP. After running into technical problems and equipment delays, such as an off-nominal re-entry, a second uncrewed Soyuz 7K TM flight test blasts off as Cosmos 672 on August 12th. The Soviets are planning to fly a manned dress rehearsal to fully ensure all systems are ready for Soyuz Apollo and a rendezvous with the Americans. The Soyuz 7K TM is heavier than its previous derivatives and takes advantage of a new generation of Soyuz rocket to compensate. The launch vehicle is called Soyuz U, and it is an up-rated variant of the original, with higher performance first and second stage engines and a redesigned launch escape system. This enables a marginal payload increase of around 200 kilograms, coupled with streamlined and modernized production techniques. Soyuz U will continue flying until 2017, with over 786 total rockets of the type launched, with a 97.3% success rate. By the summer of 1974, the man whose administration set this whole business in motion, Richard M. Nixon, 37th President of the United States, has reached the end of his political rope. Winning a landslide in 1972, largely over his foreign policy successes, things are not so good on the home front. Corruption and kickbacks catch up to his vice president, Spiro Agnew, stemming from years earlier during his tenure as the governor of Maryland, leading to his resignation from office on October 10, 1973. Grumblings of wiretapping and domestic surveillance during the 1972 election, coupled with widespread economic dissatisfaction and gas shortages due to the Arab oil embargo on the United States over its support for Israel in the Yom Kippur War, also haunt the president. The dollar is dropping in value fast against European currencies after Nixon cancels its convertibility to gold, forcing him to implement wage and price freezes and instate a wide-sweeping 10% tariff. Any one of these individual crises might have been overcome, but together they have a pogo-like effect on the Nixon administration. People are frustrated and tired, and when explosive evidence of political bugging at the Watergate Hotel emerges, Nixon's supporters and congressional Republicans abandon him in droves. On August 7th, then chairman of the Republican National Committee, future American President George Herbert Walker Bush urges Nixon to resign rather than face impeachment and removal from office. He finally does so on August 9th.
However, it has become evident to me that I no longer have a strong enough political base in the Congress to justify continuing that effort. Therefore, I shall resign the presidency effective at noon tomorrow. Vice President Ford will be sworn in as president at that hour in this office.
Occupying the vice presidency since last December is former House Minority Leader and representative of Michigan's 5th District, Gerald R. Ford. Now, he is elevated again to the most powerful office in the land, never having been elected at a national level. He is an appointed president, but his hands are largely clean of the Nixon administration's dirt. Most relevant to ASTP Ford vows to continue the Nixon administration's policy of détente and keeps Henry Kissinger on as Secretary of State. Ford even goes so far as to refuse to meet with an exiled Soviet political dissident for fear of jeopardizing the joint mission, creating considerable political pressure from both the left and the right.
Today, that freshman member from Michigan stands where Mr. Truman stood. And I must say to you that the state of the Union is not good.
In December 1974, the Soviets launch a crude dress rehearsal mission to test hardware aspects and procedural changes for ASTP. Cosmonauts Anatoly Philippchenko and Nikolai Rukavishnikov, both one-time spaceflight veterans, spend 5 days and 22.5 hours in orbit. NASA has unprecedented access to the Soviet flight, but Soviet planners do not want NASA to share details of the test with the press. They give NASA the cold shoulder and delay the communication of critical flight updates. Soyuz 16 tests the androgynous mechanical docking system, extending and retracting a docking ring and a new solar panel design for solo missions, not requiring the presence of a salute station for onboard power. They reduce the onboard air pressure and raise the partial pressure of oxygen from 20 to 40%. All tests go extremely well. On December 8, 1974, Soyuz 16 touches down in the northern Kazakh SSR. All of the major hardware components for ASTP, from a Soviet perspective, are ready to go. 1975 would be the year. No manned American space missions fly in 1974. Skylab 4, which launched in November of 1973, splashes down in February, concluding a landmark 84-day marathon mission, setting a spaceflight endurance record that would hold until 1978. But ASTP, set for the summer of 1975, would be the final launch of an American spacecraft on a traditional rocket for several decades, as NASA commits to flying the space shuttle for the next 30 years, assuming they can ever get it off the ground. Early tests don't go well, and the project is increasingly delayed. ASTP will test one aspect of the upcoming shuttle program in how it handles communication with the ground. In May of '74, a Titan 3C rocket launches Applications Technology Satellite number 6, or ATS-6. This is one of a broader lineup for experimental Earth communications applications, to be used for beaming health and educational communication nearly instantaneously across large swaths of remote areas of the Earth. It is a large satellite with an extendable 9.1 meter or 30-foot antenna with sophisticated onboard multi-frequency repeaters and precision pointing, allowing the satellite to receive and retransmit signals across several bands of the radio spectrum. ATS satellites are technology testbeds for communications, meteorological and navigations techniques, but for ASTP, it holds the promise of facilitating an unbroken spacecraft communications link with the ground. Apollo flights to the moon enjoyed very good communications coverage, ironically enough, because of their distance from the Earth. At lunar distance, as long as you're on the near side, the rotation of our planet is the predominant factor over whether or not a particular ground station radio telescope can see the spacecraft. That is not the case in low Earth orbit. Proximity to Earth, the limited radio footprint of ground stations, our planet's curvature, and the extremely high velocities of orbiting spacecraft mean that Earth orbital flights, in those days, were lucky to spend just 20% of their entire mission in communications with the ground. The LOS-AOS cycle completely dominated early human spaceflight, and it is, quite frankly, distracting. crews are spending up to half their time fiddling with their onboard radios. But NASA has an idea. If they reposition ATS-6 in a high geostationary orbit from its location over the central U.S. to a spot over Lake Victoria in Africa, they can relay communications to the Apollo through the satellite over the Atlantic and Indian Oceans, giving them not 15 to 20% communications coverage, but almost 60%. This technique is called tracking and data relay, and if successful, it is a key part of the upcoming space shuttle infrastructure, which may one day communicate with purpose-built TDRS satellites in high Earth orbit for 100% of their mission in space, even during re-entries, cutting into the amount of ionization blackout, which currently is a cost of doing business in spaceflight.
We have today, with the tracking and data relay satellite, almost full-time coverage, full-time communications, both telemetry, command and voice, video, etc., from the shuttle as it flies. In those days, the only telemetry we got was when it was over one of these little circles on the world map, which were about 5 minutes big in terms of spacecraft travel. So, and that was if you went from the maximum points on the circle. Sometimes it just skimmed the edge of the circle where you'd have 1 or 2 minutes of communication. So our brains began to be driven by, what do we need to communicate? What's our next opportunity? What do we need to get done in this pass in the way of conversations with the crew? And then what do we need to do in terms of problem solving? What do we need to do in terms of recommendations or direction to what we're going to do with the flight? So we all got tied to this little 5-minute circles that were spotted around the world where we had teams of people. We didn't even have high-speed communications that could take the telemetry and bring it back to a control center. The telemetry was all processed locally at each one of those stations, where we had a small flight control team that was like an extension of the control center, but while the crew was overhead for that station, that little team handled the whole thing. So you had to prep the team ahead of time with what you wanted to know and what you wanted to do. Often the crews would report something that was different than had been happening before, so you had to modify your plan in real time. And one of the things that caused to happen in all of us, certainly in me, was you had this tremendous sense of time sequencing and time criticality, and I must get this done by, I've only got 2 minutes, and so on and so on.
If successful, the Apollo will only spend 37% of its time in space out of contact with any ground stations, an incredible difference. Historically active S-band ground stations at Canary Islands, Honeysuckle, and Tananarive are standing down and will not be used on this mission. An expanding network of C-band stations are coming online in places like Santiago, Chile, Quito, Ecuador, and Auroral Valley, Australia. Apollo will even gather data on orbital navigation via synchronous satellite relay during the flight, attaining a total of 28 full revolutions of relay tracking data. As the mission comes down to the wire, the two crews and their backups partake in several training and goodwill trips to each other's countries.
We were, in a way, as cosmonauts and astronauts, I found out later, setting an example too, by being friendly and demonstrating cooperation. Why, I think we were helping all of the engineers on both sides feel free to be more friendly and all that. Some pretty unique things. They brought in some ponies that were used out on in the vast steppes of Siberia and all, and Kazakhstan, and we rode these ponies with Kublai Khan type headgear and robes on, and so we were racing up and down a little roadway with these ponies, and I'd ridden a lot as a kid, so it was kind of natural for me.
The American crew travels to Star City and are shown a good time. Exquisite dinners, ballet, and even the famous Russian sauna.
наверху нечем дышать. Но именно здесь нет свободных мест.
What you're seeing is a spa ritual called Venikplatsa, a leafy, aromatic bundle of birch, oak, eucalyptus, and juniper twigs soaked in hot water are gently lashed across parts of the body while in the sauna to open pores, improve circulation, and detoxify the skin. Note the operative word, gently. For their part, the Soviet crew and their senior support people come to America and visit Washington, D.C. and Disney World. Square dancing and beers and a good old Texas-style barbecue at King Ranch. Meanwhile, the two docking ports to be flown on the mission, the hydraulic American end and the mechanical Soviet end, are tested in Moscow. The American port is flown back to KSC and installed on the docking module. Engineers confirm that the two units successfully latch with each other and seal hermetically. 1974 turns to 1975, and both countries are making final preparations for the joint mission set for July. It would be a 9-day mission for the Apollo, the shortest spaceflight since Apollo 14. In February, inspections of the launch vehicle SA-210 reveals 25-centimeter cracks in the hold-down fittings on the fins of the rocket. Stress corrosion, consistent with damage also found on SA-208, the launch vehicle for the final Skylab mission. This is bad news and requires immediate attention. NASA replaces the fins and strengthens the crack-prone areas by pneumatically pounding them to induce compressive surface stress. The fins are replaced by mid-March. On March 24, 1975, the last ever rollout of a Saturn launch vehicle begins at the Kennedy Space Center.
I believe this is the 32nd Saturn vehicle that has moved from the point at which it was assembled out to the launch pad. It is also the last Saturn vehicle in the current NASA plans. So in a lot of respects, it's the end of an era. However, we look on it with nostalgia rather than with sadness, because as far as we're concerned, it's really just the end of the beginning.
as we are proceeding ahead with a lot of very elaborate plans for the next phase of our nation's exploration of space.
Thank you, Mike and Lee. Believe me, it's really a great thrill, and I thought there'd be a couple of people out to see the big thing roll out this morning, but I had no idea that I'd see all these thousands of people here. So there still is an interest in the space program, like a great interest, and we just can't thank all of you people who have worked on this great machine for all you've done for us.
I'm sure glad Charlie Buckley's going to bring us down here on launch day, because I'll never make it on my own. In my case, I've mixed emotions about the situation. After working at it for 16 years, it's great to see that thing come out the door. On the other hand, it'd sure be nice if we had another half dozen sitting there behind it ready to go also.
Thank you, Tom, Vance, and Deke. I'd like to remind you all that the launch is on the 15th of July. We expect to see you all out here then. It's about 3:40 in the afternoon, and we'll put on a truly tremendous exhibition then. So we'll see you all on the 15th of July and again in August for the Viking launch. Thanks for coming out.
On April 5th, the Soviets launch Soyuz 18, unrelated to their joint flight with the Americans, headed for Salyut 4 on a 60-day mission. About 5 minutes into the flight, when the second stage of the Soyuz rocket cuts off and the third stage begins its life, a set of locks holding the stages together fail to properly release. Still attached to the second stage, the third stage engine lights, blasting directly into it and causing the large stack to begin tumbling in space. This off-nominal attitude triggers the onboard abort system, which immediately cuts off the third stage and separates the Soyuz spacecraft for an about-face abort and immediate return to Earth. The two cosmonauts aboard, Vasily Lazarev and Oleg Makarov, experience a crushing 21G re-entry as they plummet steeply down at over 10,000 miles an hour. Slower than a normal re-entry, but much steeper, meaning the spacecraft hits thick atmosphere much earlier in the time frame and therefore experiences debilitating levels of aerodynamic deceleration. The pressure is so intense, it inflicts permanent spinal damage to Lazarev, who will never fly into space again. The incident comes at a terrifically embarrassing time for the Soviets, whose manned spaceflights are under an intense international spotlight. They can't just cover this one up. External scrutiny is at an all-time high. They have to explain, hat in hand, to NASA what went wrong and what fixes will be implemented to assure their new American friends that there is no reason to lose confidence in the Soyuz hardware. Konstantin Bushiev, Soviet technical director, calls his counterpart Glenn Lunny and explains that the launch vehicle used on what would become known as the April 5th incident was not the same version planned for the July ASTP launch, and that upgraded relay switches involved in the staging process were to be installed ahead of time. Never short of fresh hardware, the Soviets would try again on Soyuz 18, flying just a month and a half later with brand new hardware and a new crew. The Soviets are so flush with Soyuz and Salyut vehicles, a world apart from the experience of NASA in the mid-1970s, which finds itself almost entirely depleted. After this flight, it would be a long 6 years before American astronauts would fly into space again. The United States would not be without its own embarrassment in April of 1975, but it has nothing to do with its space program. The last American helicopters depart the roof of the U.S. Embassy in a chaotic withdrawal as the North Vietnamese Army closes in on Saigon, the capital of South Vietnam. For the Vietnamese, it is the closing of one very long chapter of suffering and the opening of another. For the Americans, images of U.S. helicopters evacuating Saigon amongst panicked crowds is a brutal kick in the teeth for the image of a nation struggling economically at home, and of the sacrifice made in time and blood of the over 2.7 million young Americans who had been deployed there, 1/3 of whom were drafted. Whatever powerful a positive image the meeting up in space of American astronauts with Soviet cosmonauts could be, an equally powerful negative image generated just 3 months earlier makes the mid-1970s a time looked back on with a general sense of malaise. Confidence in political leadership is at an all-time low. The command module computer on ASTP is flying with the late Earth orbital post-lunar Skylark programming on board, with ASTP-specific erasable memory loads. Some of the Skylab changes includes new capabilities such as jet-on monitoring, which oversees the spacecraft attitude during sleep periods and triggers a master alarm if the spacecraft drifts out of a programmable deadband, which might be an indication of a thruster leak. 3 major ASTP-specific programs are loaded. One maneuvers the spacecraft through a predefined raster scan in order to support an onboard extreme ultraviolet telescope that will be operated by the crew. Another produces fixed-length 2-jet translation impulses through the translation hand controller, a special control mode patch made specifically for the joint mission. And lastly, a third program computes pointing angles for the Apollo spacecraft steerable S-band antenna, enabling it to achieve a lock on the ATS-6 satellite in high geosynchronous orbit. The steerable high-gain antenna, a part of Apollo's lunar missions but absent from the Skylab flights, is back again for this reason. Every aspect of this flight is rehearsed and choreographed on the ground. Everything. Even the opening of hatches and shaking of hands. Where to place the TV cameras, and what to say when it all goes down. Nothing is left to chance. No room for improv. Zero guesswork. The political leaders make sure they already know exactly what they'll be getting before it ever even happens. The mission support personnel are rigorously tested. Multi-day simulations in May, ranging from 25 hours to over 56 hours at a time, run through rendezvous, docking, and crew transfer procedures. 2 nations operating as one. 2 space agencies combining their talents for something greater, something higher. One humanity. For the first time ever, a television camera mounted inside the Apollo spacecraft cabin will be broadcasting live images from the interior during the launch. Commander Tom Stafford is no stranger to television in spaceflight. His work on Apollo 10, the first mission to carry a color television camera into space, earned him an award from the National Academy of Television Arts and Sciences. He is what you might call camera-friendly, and that is just another reason why he is perfect for this mission. The point of which, to a large extent, is to televise a highly political moment. Both live and recorded TV will be conducted on this flight, with no fewer than 4 Westinghouse color TV cameras being flown on the Apollo side alone, not to mention the Soviets. Bob Schaefer and others in NASA's Press Affairs Office work to ensure ASTP is the most thoroughly televised spaceflight in history up to that point in time. Senator William Proxmire, Democrat from Wisconsin, attempts to intervene at the last minute, pushing NASA to delay the mission until the conclusion of Soyuz 18, currently aboard Salyut 4, citing safety concerns over whether or not Soviet mission control could handle the 2 missions at once. His attempt for delay is unsuccessful. July 15th, 1975, 3:20 p.m. Moscow time, 8:20 a.m. Eastern Time. Leonov and Kubasov and their Soyuz are the first to fly.
ускорения не ощущается. Легкое покачивание. Слышу вас бодрый голос, 30 секунд, полет нормальный. Единица самочувствие нормальное. 40 секунд, полет нормальный. В борту все нормально, давление в норме. Отлично. ГС-1 из ПГС-2 держится в норме. Отлично. 120 секунд. Отделились боковые блоки первой ступени. Скорость ракеты более 1,5 километров в секунду. Двигатели второй ступени работают устойчиво. Чувствуется незначительная перегрузка. ...160 секунд. Сброшена система аварийного спасения. Разошлись створки головного обтекателя. Секунд полета. Ракета идет устойчиво. Скорость ее превысила 3 километра в секунду. секунд. Произошло выключение двигателя третьей ступени. Союзы, я 16-3. Стабилизация нормально у вас? Нормально. Вроде бы нормально. Все товарищи вас водопол моргали, погасили. Снег стабилизирован. Контролируем давление сил. Все товарищи вас поздравляют с успешным выходом на орбиту и началом работы. Успеха вам! Спасибо, сила в норме. Спасибо большое. Начинаем работать. Сейчас 20-й еще с вами хочет поговорить. Минутку, послушайте его. Союзы, я 20-й. Как слышите? Прием. Да, слышим отлично, 20-й. Хорошо слышим. Ну, дорогие союзы, поздравляем вас сердечно, обнимаем и целуем крепко. Поздравляем с выходом на орбиту. Желаю вам успешного выполнения программы и счастливого полета.
Soyuz 19 is in orbit of the Earth. 5 hours later, they begin the process of dumping pressure to 0.68 atmospheres as they await the launch of the Americans. They perform a 7-second burn. The 7-second trim firing of the primary propulsion system places the Soyuz in what is termed in ASTP parlance as the, quote, assembly orbit. Everything is in place, and now it's NASA's turn up at the plate.
This is Apollo Saturn Launch Control. We're T-minus 3 hours, 16 minutes, and counting. At this time, we're standing by for the astronaut crew to leave the manned spacecraft operations building. And at this time, the crew is coming out the doors at the manned spacecraft operations building. Tom Stafford, crew commander, leading the way, followed by Vance Brand and Deke Slayton. All three men in their spacesuits and carrying portable oxygen ventilators. Stafford reports he has made the final GDC align. First stage, second stage, and instrument unit now on internal power. Approaching the 30-second mark in our countdown, water pouring onto the flame deflector, now coming onto the deck of the mobile launcher. Everything proceeding smoothly. We'll get a guidance release at the 17-second mark.
20 seconds.
The engines will actually start. Engine sequence starts at 3.1 seconds in the countdown. We'll hold down till thrust builds up.
11.
Engine
10,
ready light on.
9,
10, 9,
8,
8, 7, 6, 5, 4, 3, 2, engine sequence start. 1, 0, launch commit. We have a liftoff. All engines building up the thrust. Moving out. Clear the tower.
Roger, tower clear. Roger, Tom, you got good thrust on all engines. You're right on the money. Roger, I got a roll program. Started, but not much. Roger, Tom? Yeah, she goes, pitch program, little shaky lift off, but it's smooth as silk now, Okay.
Saturn launch vehicle beginning a 45-second maneuver to the proper roll. Trajectory looking good.
30 seconds and we're on the way. Roger, Tom, you're looking real fine.
Coming up on 1 minute, we're clear of the beach. Follow now 3 miles in altitude, 1 mile downrange.
Stand by for mode 1 Bravo. Mark, 1 Bravo. 1 Bravo, 2 Gs. Roger. Cabin pressure's coming down. Roger.
Cabin pressure relieving as expected, coming up on the region of maximum dynamic pressure.
CDS auto off, 2 inches auto, LB right side. And we got an SMRCS A light on.
And Pete Frank getting a status for staging. Go for staging.
Houston, you're go for staging. Go for staging.
And we have a report that we are losing some data here in the control center. We've lost data from the command module computer. Trajectory still looking good.
Roger, Tom. Okay, and the flight is out on the 4B. Roger, give it acceleration.
Capcom Dick Truly advising the crew that everything looks good on the Saturn second stage.
Tower jet, there she goes. Roger, tower jet, you're in your mode.
And the launch tower no longer needed, has been jettisoned as planned.
And we got some beautiful sight. Roger, wish I could see it. Roger. Yeah, this is worth waiting 16 years for. Got a beautiful I here, Dick. Roger, I believe all of that.
And Flight Director Pete Frank getting the advisory that we look right on. Everything looks good.
A Saturn 1B launch, which is the booster we had. Saturn 1B is what we had for Apollo-Soyuz. It's very similar to a shuttle launch. I think it took something like 9.5 minutes to get into orbit on a Saturn 1B, and on the shuttle it takes 8.5 or something like that. But on both you have staging at a little over 2 minutes, and you start out with a lot of shake, rattle, and roll just after the engine's light on the pad, and you're lying down looking more or less straight up on each. And when staging occurs, why there are some sort of pyrotechnic events that happen, and you may be aware that you're getting separation and all that. And then on the second stage, everything smooths out. You don't have the shake, rattle, and roll so much. It's more like going on overdrive.
We go! Roger. And we're right in there. We is here. According to the computer, in an 89.4 by 83.1. We know Hodemson our beaching.
7 hours and 30 minutes after launch, 3:50 p.m. Eastern Time. Apollo nails it on the first opportunity. 1 hour and 14 minutes later, Apollo separates from its S-4B booster. Again, in this instance, the ASTP hardware is more similar to the lunar missions than the Skylab missions. On Skylab, since there was nothing to extract from the depleted stage, the 4 spacecraft lunar adapter panels remained attached like on Apollo 7. This time, however, because the crew must retrieve their docking module, the panels jettison outwards, 4 large pieces that will eventually decay and re-enter, burning up in the process. The S-4B would remotely initiate a deorbit maneuver at 5 hours and 15 minutes.
Oh, super. God damn. Okay, you're coming around pretty good. Look at the panel. That panel's really going away. Look at that. Look at that ocean. Okay, you might check your monitor. I'm looking at it. All I'm seeing is clouds. Looks all right to me. Okay, there he is.
Okay, I got full bright on that coax.
He's right out there where he ought to be.
Good shot. Super. Okay. I can't, God damn, how did we ever get in this attitude? I can't see my coax. I can't see the so bright I can't see the coax. Son of a bitch. Okay, we closed on him. Let's get this.
Did you do plus X 3 seconds?
Yeah.
Okay.
Oh, shit.
The problem is, with Earth so bright in the background, none of them can actually see the illuminated reticle on the angled glass plate called the combiner.
And if you need the camera ever, let me know.
No, I'm too busy.
Okay.
Oh, that scared the hell out of me.
I think we hit the hand controller.
Okay, stand by.
Okay.
Hey, don't say, let me just concentrate on this mother. Got contact?
Capture. CMC free.
CMC free.
No, CMC free.
CMC free.
Okay. Good.
Stand by or retract it.
Give her
roll,
10 seconds.
Roll looks beautiful. Roll is right on.
Okay. When you're ready, I'll retract.
Okay, retract her.
Retract.
Crunch. And we got a hard dock.
Oh, man. Good deal.
That is hard. All right, Jesus. Correct.
Okay, we got talkbags gray. It's beautiful.
Man,
Okay.
this thing is zero. Right on.
Okay, extend release is coming off. And retract is off. I just didn't realize the big difference between your window and mine. That's why I was telling you, watch it keep coming. Because it was going out of my window.
Yeah.
I was, and I guess probably then we hit the hand controller and that gave us the off attitude.
All righty, beautiful.
Okay, we're there.
Okay, you want it to go a little bit right? All right. Go.
Now.
We're moving
CMC
out.
auto.
Super. CMC auto. They're moving out.
Moving out. Okay.
That's beautiful.
I'll take
5
some
seconds,
samples.
I thrust minus X.
Okay. That is beautiful, isn't it?
Yeah. Well, that's a big milestone. Let me get that out of plane on here, too. And we got a good docking module with us, man.
Yeah. Our own thrusters make light, apparently.
Oh, sure.
Yeah. Look at that big Earth.
With the DM successfully extracted, the crew commences to removing the docking probe from the command module's docking tunnel, now no longer needed, a mere obstruction. But improperly installed, misrouted pyrotechnic connector cables on the probe prevent the crew from using the normal tools in removing it.
All right, no, we got a problem. We can't get the probe out to stick that wonderful little freezer up there.
They will not address it on the first day, waiting for the always dependable crackerjack minds of Mission Control to come up with a fix. On Flight Day 2, they will have to remove the pyro covers and disconnect the incorrect wiring.
We had a lot of work to do. We had to go through many steps, each one of which had to be successful. So after you achieve orbit, you set up camp, so to speak. Now that you're on a spacecraft that's turned out from being a launch vehicle to being something that sits on orbit as a platform for useful work. In the 2 days before docking, we did what was in Apollo called the transposition and docking maneuver, which was essentially detaching the command and service module from the booster, going out 50 feet or so, turning around, coming back, docking with the docking module, which was inside a canister at the end of the booster, pulling it out. We pulled the docking module out, and then we departed the booster, and it eventually re-entered. We started making burns that would get us synchronized with the Soviet spacecraft so that we could continue with the latter phases of a rendezvous. The first burn or two gave us a catch-up rate. They were way ahead of us in orbit, the Soyuz was, and with cosmonauts. And so we spent about a day and a half just catching up with them in a lower orbit that had us going around the Earth in a shorter time than they were.
Ground elapsed time 18 hours 39 minutes. The Apollo crew has been asleep now for not quite 2 hours after reporting a problem in removing the probe in the command module tunnel.
At the conclusion of the press conference, we join the current ATS-6 satellite pass, which has 37 minutes remaining. Vance Brand is now well underway in correcting the probe problem. He has the cap back on, the offending connector for the pyro.
It will take some 50-odd hours for the Apollo to catch up with the Soyuz. Both vehicles traveling nearly 8 kilometers every second around the Earth. Round and round they go. Stafford, Brand, and Slayton give a long, nearly 9-second pulse of the spacecraft's RCS engines, their first notable maneuver of many in space to establish a separation between themselves and the booster. Just an hour later, they shoot a blurp through the service propulsion system engine of less than a second to circularize their orbit, raising their periapsis from 150 kilometers to 167. And over the course of the next 2 days, the Apollo, as the first active rendezvous vehicle, would make a long series of very short burns, many of which last no more than a second or two. Little shoves and nudges as they inch ever closer to the Soviets. First phasing maneuver. Phase correction, second phasing, corrective combination, co-elliptic, mid-course, and terminal phase. The spacecraft was flying through everything they could throw at it. The final Apollo ever to be launched was a healthy horse indeed. The ASTP flight is absolutely chock full of science. This was, after all, NASA's last chance to fly experiments on a manned spacecraft for the foreseeable future. With shuttle lagging behind, no one knows how long it will take. This is an opportunity to follow up and fly anything not covered or worth a second glance after the extended Earth orbital missions of Skylab. And there's no shortage of ideas. Earth observation and photography is one such field, and the American crew will spend a considerable amount of time on this mission studying pre-selected areas of Earth, recording their appearance with film cameras and speaking into the spacecraft's onboard tape recorder on what they can see from space from a much lower altitude than Skylab. They will look into strike-slip fault zones, study ocean waves and oil slicks, red tide, and the pollution around major cities. It is during this time that the crew reports the presence of a mosquito in the cabin of the Apollo. This insect, somehow, has evaded notice and has survived into orbit. But it subsequently will disappear and is never seen again. Everything was going well. They open the hatches to the inside of the docking module and discover an odor like burnt glue or acetate emanating from within. The smell is so strong and so bad, Commander Stafford has pilot Brand go on emergency oxygen flow inside the spacecraft, and the crew even dons masks. Besides some annoying interference with the ground, everything is going pretty well. There are minor hardware failures common to all spaceflights in both the Soyuz and the Apollo, primarily in instrumentation displays. Tank quantity measurements and temperature transducers in the cryo-O2 and helium pressure tanks. Minor issues, annoying, but not showstoppers. The ATS satellite relay is working. The crew activates yet more experiments, both in the command module and in the service module. On July 17th, at 3 a.m. Eastern Time, they establish direct radio contact with Soyuz 19.
As we got close to them, eventually, probably, I don't know if it's exact, but possibly about 500 miles out or so from them, we started looking for them with our optics. And I eventually saw them through the telescope as just a white, bright dot against the black background. And so when we located them, then our computer was used to make computations of, was the ground right and our catch-up rate and all that sort of thing. And eventually we had another sensor, which was a range rate sensor, which locked onto them, and so our computer was updated with good navigation information.
Flight Day 3, Rendezvous Day. Starting at 42 hours and onward, spurious master alarms would commence, indicating the failure of an inertial coupling data unit, or ICDU. Some 27 program alarms related to the inertial subsystem would be triggered over the course of the mission, but in-flight and ground-based tests of the system showed it to be functioning well. The cause of the failure is never determined, and like so many of the others mentioned, seeing as this was the last flight of an Apollo vehicle, no corrective action would be taken.
Hey, Dick, we've got Soyuz in the sextant.
Hey, super. Have you got a good view of him, Vance?
He's just a speck right now.
There she is, Soyuz 19.
Aha. Here he comes, just above the docking module. Looks real pretty.
The Russian spacecraft goes to its programmed inertial attitude and pitch, tracking the horizon with infrared scanners. Tom Stafford is hand-flying the Apollo.
Apollo, Houston, I got two messages for you. Moscow is go for docking. Houston is go for docking. It's up to you guys. Have fun.
All righty, sounds good. Polovina, Mila, Alexei.
Roger. 800 meters. Sorry. Miles. What is the range rate?
Очень хорошо. 80 секунды.
Tom Stafford reported from Apollo that he was beginning the braking maneuvers to go into station keeping with Soyuz at from 20 to 50 meters distance. Both control centers, Moscow and Houston, have given a go for docking at the usual, or the flight plan time. President Ford will place a call to the crew of Apollo and Soyuz, speaking to Tom Stafford and Alexei Leonov aboard Soyuz after the first transfer has been completed. This will take place at about 2:30 Central Daylight Time. We should be getting acquisition momentarily through the ATS-6 satellite.
3 meters. 1 meter. Contact. Capture. We also have capture. We have succeeded. Everything is excellent.
Soyuz and Apollo are shaking hands now.
We agree.
Copied, Alexei, seeing you're holding hands, and we see it too.
Москва, я Союз 2, как слышите, прием.
Союз, Аполлон, начинаю стягивание. Soyuz, this is Apollo. Initiating retraction. Houston, Apollo.
Go ahead, Tom.
Говорит Professor Bushoyev into Mayaki Stakovka. It was a soft docking. Tell Professor Bushoyev it was a soft docking. Stakovka, выполнено. Docking completed. Docking is completed, Houston.
Roger. Москва, я Союз 2, как слышите, прием. Well done, Tom. It was a good show. They are looking forward now to shaking hands with you in both Soyuz.
Спасибо, Alexei. Thank you, Alexei. Спасибо очень. Thank you very much. To you and Valery.
The docking rings brush up against each other. Stafford fires a +X pulse, driving the hard capture latches in. Ka-chunk. Half an hour after docking, Apollo astronauts Stafford and Slayton enter the DM, closing the hatches and isolating Brand, preparing themselves for the political highlight that many hope will come to define a generation. Two nuclear superpowers at opposite ends of the ideological spectrum, coexisting peacefully above a bipolar world. It will be a whole 3 hours before the hatches to the Soyuz can open. Leonov and Kubasov are running behind, and the iconic handshake moment will occur an hour and a half behind the intended schedule. They exchange greetings with the cosmonauts aboard Salyut 4 over the radio, and at 3:17 p.m. Eastern Time on July 17th, 1975, the hatch between two countries is opened in space.
Soyuz, Apollo.
Soyuz, this is Apollo. Now hatch 4 is open, over. Roger, roger. Hello.
Glad to see you. Here.
Very, very happy to see you. This is the Soyuz and the United States. Valery. Come here. Valery, how are things?
After all of the political posturing, the negotiations, and the give and take, and the treaty signing, all of it boils down to a handshake in space that symbolizes the desires of both nations to put the worst of the Cold War behind them. Despite all the outstanding issues and unsolved challenges, on a personal level, this training and this flight helps a new friendship blossom. Very well documented is the lifelong camaraderie between Tom Stafford and Alexei Leonov that will endure long after this mission is done and dusted. They would correspond regularly, meet up as much as they could. It would go so far as to the point that Leonov would be the godfather to Tom's later children, a family dynamic that stretches across borders and political lines. There are few things on this planet, and in this case, even off this planet, as precious as a lifelong friend.
The astronauts are on the line, sir. Gentlemen, let me call to express my very great admiration
For your hard work, your total dedication in preparing for this first joint flight.
It's taken us many years to open this door to useful cooperation in space between our two countries. And I'm confident that the day is not far off when space missions made possible
by this first joint effort will be more or less commonplace.
And may I say, in signing off,
here's to a soft landing.
This crew has trained together for this flight for many, many months. They know each other well and, in a professional context, can predict each other's moves and can operate as a cohesive team. Military men all, having trained just years earlier to shoot each other down. They exchange trinkets and symbolic items. 5 U.S. flags exchanged for 5 USSR flags. 2 commemorative plaques broken into halves, joined together for the first time in space. A permanent symbol of the first international human spaceflight. Documents to be signed. The 2 spacecraft will remain connected for the next 2 days. After Stafford and Slayton spend 3.5 hours inside Soyuz, they are back in the docking module and both crews sleep. Tomorrow would be a very busy day.
Houston, Apollo.
Go ahead, Tom.
Hey, how about doing me a favor, Dick? Check with the flight planners and the stores. find out where the bracket is that we mount the 300 millimeter Nikon lens out the right window?
Okay, sure, we'll do it. Probably at the tail end of this ad space, if you guys will give us a good idea as to where you are, we can, we'll try to help you out on the flight plan.
July 18th, 1975. Flight Day 4. Stafford and Brand this time enter the docking module, and after an hour of equalization, the hatches to the Soyuz are opened. Brand enters the Soyuz with Kubasov, while Leonov joins Stafford in the docking module. They button up the hatches again, and after yet another hour, it's Leonov, Stafford, and Slayton in the Apollo, with Brand and Kubasov in the Soyuz. Today is a work day, and the mixed-up crews are busy doing their science experiments.
Houston, Apollo.
Apollo, Houston, go ahead.
Yeah, Bo, are you getting any picture in the Soyuz now in the orbital module? All I can get on my monitor is just a screen that's really brightened out.
Right now we're looking at one down through the hatch, and we see that quite well. The other camera we were getting a picture on, but you're often in front of it, but that's just supposed to be a stowage location for that camera.
Okay.
Command module, Houston, could we have you open the lens on your TV camera wide open?
Science aboard ASTP, political a flight as it was, should not be discounted. The first ever discovered pulsar outside of our galaxy was discovered with data taken by the soft X-ray experiment. Located in a binary star system in the small Magellanic Cloud, some 200,000 light-years away, SMC-X1 is at the time the most luminous pulsar ever discovered, radiating X-ray energies greater than 2 kiloelectron volts, with a period of only 0.7 of a second. The crew also discovers soft X-ray emissions from the supernova remnant MSH 1463. Stellar objects such as neutron stars and black holes were purely theoretical just 10 years earlier. Space science has been revolutionized in that time, and Apollo-Soyuz rides high on the crest of the waves created by mankind's first big splashes out into the universe. It is the closing of a golden chapter of human spaceflight. The crew also performs the extreme ultraviolet experiment, which exists on the electromagnetic spectrum just below the so-called soft X-rays. A survey instrument mounted in the service module of the Apollo spacecraft consists of 4 concentric grazing incidence mirrors, which feed cosmic radiation through filters to an electronic detector tuned to the extreme ultraviolet. They use a specialized onboard computer program made specifically for this flight to undergo a series of automatic pointing maneuvers aiming the instrument at a variety of ultraviolet radiation sources in the 50 to 1000 angstrom range. EUV from 4 stars was positively detected, including 2 very hot nearby white dwarf stars that, it is inferred from the readings gathered, are in excess of 100,000 degrees Kelvin.
Hey, Alexei, good job. Hello. Oh, howdy, partners, my old friend. Here we go. What is my place? Well, for now, come right into here. Okay. Так. Good morning. Okay. So I'm just there. Oh, well, how are you?
Hey, by the way, if you're looking, Bo, there's Valeri's family. His wife, Ludmilla, and 2 children, daughter, son. Let's see, it's Kat, Say that.
Roger, we can see Ludmila and Katya.
Ludmila and Katya. Dmitri, yeah, that's it. The boy, the youngest, is Dmitri. Good-looking family, huh?
Hello, American people. The first Soviet-American TV center in space. That's working on board the docked Apollo-Soyuz spacecraft. I am going to tell you about Soyuz spacecraft. The Soyuz spacecraft consists of some compartments. The orbital module, descent vehicle, the instrument assembly unit, and propulsion system. The propulsion system has one main single-chamber engine and two-chamber backup engine. These engines are used for maneuvering in orbit and deorbiting at the end of the mission. The purpose of the panel is to control and monitor the orbital module system. These are the following: environmental control system, the TV and illumination system, the radio system, and the other some systems.
The crew measures aerosols in the Earth's stratosphere, finding the concentration 2 times greater in the northern hemisphere than in the southern hemisphere, and tightens the error margins made in a number of other fields, such as helium glow and closed-eye light flashing. One experiment, called BioStack, subjects dormant cells of plant seeds and brine shrimp eggs to particle effects. Similarly, radiation effects upon a fungal bacterial cell will provide a baseline against control groups on Earth as scientists measure the culture growth post-flight. There is also a litany of human biology experiments, further investigating the effects of spaceflight on the human immune system. It is the experience aboard Skylab that while the number of microbe strains in the human body diminishes in flight over time, the population of microbes of those surviving types increases significantly in the human body. Over the course of extended spaceflight, the human immune system changes. The crew will take skin swabs in flight and provide blood samples before and after the mission. Electrophoresis, or the separation of biological materials by means of an electric field, is also studied in space. A 30-pound setup containing 4 test columns of red blood cells, 2 of lymphocytes, and 2 of kidney cells in 5-inch glass tubes subject those cells to an electric field in microgravity. ASTP also carries aboard an electric furnace of a similar type demonstrated on Skylab. Located inside the docking module, the furnace, its heat sink assembly, and vacuum line will be used to melt a variety of metal alloys and then allow them to cool slowly in the zero-G environment, after which their crystal structures will be examined on the ground. The furnace allows NASA to conduct cutting-edge materials science, the presence of which just 10 years ago would have made space planners balk. After 4 hours and 45 minutes, Stafford and Leonov exit the Apollo and entered the docking module. After a repressurization period, they swap places with Brand and Kubasov, passing each other. The hatches are again closed, and now it is Slayton, Brand, and Kubasov in the Apollo, with Stafford and Leonov in the Soyuz.
Docking module pilot Houston.
Okay.
When you did the experiment active putting it into the furnace, did you do steps 8, 9, and 10 on page 7.2 of the docking module?
Yes, affirmative.
Understand.
Okay, both you read, we're both back into DM and the hatch is going locked.
Roger, understand, you're in a DM.
Last use of the Apollo equipment was a thing to stop and think about. It had been equipment that had been developed to go to the moon and had been very successfully used. It showed it was equipment that was developed by probably hundreds of thousands of people that were behind the Apollo program, and yeah, here it is, the last usage. Too bad we can't take it back to the moon for a few more times or use it. But at that time, of course, we had the space shuttle just starting its development. So everybody was saying, well, but we won't have to land in the water anymore. We'll have a craft that you can land with, like an airplane, and that'll be better. So everybody was a little sad, but at the same time looking to the future and a more improved system, we hoped. I must say, though, that there were things about the Apollo equipment that were not as good as the shuttle, but there were some things that were probably better, like the Rendezvous software in the computer. It could complete a rendezvous from beginning to end, whereas in the shuttle you depend on the ground until the very last part of the rendezvous. You depend on them to give you your navigation and guidance, and then the computer, onboard computer, takes over. So the Apollo equipment could actually was more independent of the ground in a way.
2.5 hours later, Slayton and Kubasov enter the docking module, leaving Brand behind in the Apollo, and join Leonov and Stafford in the Soyuz. This is to be their final time together, as the joint intravehicular period of this mission is already coming to an end. The crews go back home, and the hatches are closed for the final time. After a long night's sleep, Soyuz 19 and Apollo undock at 7 a.m. on the 19th of July and begin station keeping with each other. While the crews will not be physically meeting up again, there are still experiments and tests to be run between the two spacecraft working in proximity.
Apollo Houston through, that's over.
Roger, Bo, read you loud and clear.
Roger, you have a go for undock. On panel 230, we would like the up telemetry switch to relay.
Roger, we've undocked at station keeping. Everything was on time, Bo.
Soyuz orientation lights on.
Lost volume. How's your picture on the tube, Bo?
Pretty good. We see Soyuz there, and understand the picture's even going to get better as we get into the daylight. Apollo Houston, the TV picture is so good we can see the capture latches.
Roger, Bo, roger. Okay, the Deke has the same problem I have. The coax is completely washed out. It's full up. It's so bright out here.
Understand.
We can look at ballpark. It's about 50 meters, plus or minus 1 or 2.
Roger.
The quantities of atomic oxygen and atomic nitrogen at orbital altitude are measured with an instrument aboard the Apollo that bounces a laser beam to a retroreflector on the Soyuz and then measures what returns. This beam of light has wavelengths corresponding to neutral atomic oxygen, and measurements are made at separation distances ranging from 150 meters up to a kilometer.
And, Bo, we think maybe his docking attitude isn't exactly what we've got on the pan. I'll give you our docking attitude as soon as we have it refined here.
Roger. Apollo, Houston, on the out the window camera, we'd like you to go to linear again, please.
Then, the Apollo moves to block out the sun from the perspective of the Soyuz, generating an artificial solar eclipse that will allow Leonov and Kubasov to photograph the solar corona from space as it existed in 1975. The results are mixed, and seem to communicate more about the gases emitted by the spacecraft, backlit by sunlight, than they do about the sun's own atmosphere.
In all of the history of spaceflight, there have been a great many firsts, and there have been some firsts on this Apollo-Soyuz mission. The first joint flight with docking and crew transfer of spacecraft between two nations. There have also been a great many lasts in Apollo-Soyuz. It's the last flight of the Apollo-type spacecraft. It will be the last water landing of a U.S. spacecraft. Be the last use of parachutes for a U.S. manned spacecraft landing. And the launch on the 15th was the last flight by any of the Saturn family of launch vehicles.
Now, as a final test, the mechanical Soyuz docking port is switched into the active mode, and the American port is switched into its passive mode. And this time, Deke Slayton is at the controls. He hits it at a higher relative velocity than did Stafford on the first docking. Bang! The two docking systems are brought together hard and successfully capture. The American crew nervously watches the entire system oscillate and flex, the solar panels of the Soyuz wobbling. The Apollo crew goes CMC free and lets the spacecraft drift out of attitude as the oscillations dampen. Everyone breathes out and takes a break for lunch. 3 hours later, Leonov and Kubasov actively undock from the Apollo for the final time. After 3 hours of station keeping, Apollo fires its reaction control system and moves away at 2:42 p.m. Eastern Time on the 19th. They maintain direct radio contact with Soyuz 19 until the respective distance between the two vehicles is too great, even for the VHF.
After the final undocking, they were in a went to a lower orbit and speeded up and went ahead of us. We tried to play a little joke on them at that point. Before the mission on the ground, I had made a tape at home of, and my daughter Stephanie and a friend helped me make it. We turned on shower water, and they weren't in a shower, but it sounded like it. Both girls were about 18 or 19 years old, and so they made a lot of noise, which made it sound like somebody was in a shower just having a ball, a lot of giggling and stuff. And after the Russians were ahead of us 400 miles, and we had watched them go out ahead of us and probably tracked them a little bit, why we played this tape and over the VHF communications, which both spacecraft had, and we said, "Hey, we're having a ball here," and then we played this noise. "What are you guys doing?" And there were all these female voices and stuff, and so I'm not sure that they heard that tape actually, because after the mission, Alexei was asked, and he didn't act like he knew about it, but we tried anyway to to play a little joke on them.
Over the next 2 days, the vehicles would continue operating their own onboard experiments. The Apollo crew continues working with the furnace in the docking module still attached and operates the X-ray instrument. Their TV cameras seem to be deteriorating, losing color and experiencing spurious flashes. More instrumentation troubles pop up, including the primary evaporator inlet temperature reading, failing off-scale high. The caution and warning tone becomes so quiet as to be inaudible by the crew. At 141 hours and 50 minutes after Soyuz launch, Monday, July 21st, Leonov and Kubasov, having test-fired their Soyuz primary engine the previous day, initiate their re-entry retrofire burn of a little over 3 minutes duration, slowing them down by 120 meters per second and sending them on a course to a touchdown on land 90 kilometers northeast of Arkalik in the Kazakh SSR.
Moscow, this is Soyuz. We have engine fire. Stabilization is stable.
We show that their deorbit burn began at 5:10 and 35 seconds a.m. Central Daylight Time. Soyuz crew reported at least a 2-minute burn.
The Soyuz spacecraft at this time uses the KTDU-35 propulsion system, which includes a one-chamber engine, the large hole you see in the center, as the primary propulsion method that burns unsymmetrical dimethylhydrazine, or UDMH, and an oxidizer called AK-27I, a mixture of 73% nitric acid and 27% dinitrogen tetroxide, with an iodine compound added as a chemical inhibitor. This is powerful, nasty stuff. The iodine inhibitor is there to prevent the potent oxidizer from corroding the fuel tanks from the inside out. The tanks themselves are rubber bladder-type tanks like the Americans used on the Mariner spacecraft, but the engine is operated on an open gas generator cycle. A dedicated gas generator siphons off a small amount of the propellant to generate high-pressure gas which powers turbopumps that delivers the main stream of propellants to the rocket engine combustion chamber. The turbopump exhaust is piped out through the 4 outer holes you can see. The primary system develops 919 pounds force, or just over 4 kilonewtons of thrust, with a specific impulse of 280 seconds. You may notice, however, there are 2 holes in this picture left unexplained. Those 2 nozzles on either side of the primary engine belong to the twin-chamber emergency backup engine, a one-shot, non-restartable, non-throttling, steerable retro-fire engine with its own independent propellant feed system, capable of deorbiting the Soyuz spacecraft even if its main propulsion unit and all of its RCS attitude thrusters fail. A last resort punch-out from orbital flight, only ever activated if something has gone seriously wrong.
Separation of the modules of the Soyuz spacecraft has taken place. This data was received by signals transmitted from the orbital module of the spacecraft Soyuz. Soyuz, this is Moscow. I can hear you. Roger. Everything on board is normal. Separation was on time. Descent rate approximately 7 to 8 meters per second. The descent rate of the spacecraft, 1,000 meter altitude. Moscow time 13 hours, 48 minutes. Contact of the descent vehicle at 13 hours, 50 minutes, 54 seconds Moscow time. The parachute has been jettisoned. The soft landing engines fired and a small cloud of dust rose. The descent vehicle is lying on its side and the helicopters of the rescue unit are approaching it. Commander of the spacecraft, Alexei Leonov, has just exited from the spacecraft. Moscow time at that time was 13 hours, 54 minutes, 25 seconds.
Alexei Leonov waving at the rescue team members, apparently in very good spirits.
Solid propellant, soft landing jets fire just feet above the ground, slowing the vehicle just before impact. The cosmonauts undergo a hard-hitting double thump of the rockets followed by the touchdown, and this allows Soyuz, a non-winged vehicle, to touch down anywhere on Earth. Leonov and Kubasov exit their vehicle triumphant heroes, returned from space.
We'll time it.
Roger, the second one is at 1:44:40. And that's changed the high gain angles to -4 and yaw 312. And that's a change to the change.
The crew prepares to jettison the docking module, now full of garbage and other items not intended to be brought back home. Prior to separation, Brand reports that the attitude ball on FDAI-1 does not consistently flip to orbital attitude when the orbital rate 1 switch was set from inertial to orb rate. And when it did flip, it did not always indicate the correct attitude. After the flight, NASA figures that there are 4 possible failure mechanisms that might have caused this anomaly. But since the upcoming space shuttle will not have an orbital drive rate assembly, they do not investigate any further beyond educated speculation. The separation from the docking module will be highly unusual and is driven by a science experiment. NASA wants to use Doppler tracking between 2 objects at a lower orbital altitude, in this case, the Apollo spacecraft and the jettisoned docking module, to map minute velocity changes caused by mass concentrations in Earth's crust. The existence of mass cons around the Moon had a profound effect on lunar mission profile planning. They intend to measure, by means of a phase-coherent, dual-frequency VHF link, the Doppler shift between the DM and the CSM after separation. But there's a problem. The docking module, on its own, has no attitude control. Random torquing by mass cons or plume interactions from Apollo RCS bursts could cause it to drift this way and that in an unpredictable, chaotic fashion that could poison the data, smearing attitude errors into the same kind of low-frequency range rate variations that the experiment was trying to attribute to gravity. So, some smart cookies on the ground have a bright idea. Spin it up. A known fast spin would push much of that data contamination into a recognizable pattern that could be corrected for in the post-flight analysis. And so it was, for the only time in Apollo, in fact, the only time in human spaceflight history, that an entire spacecraft was entered into a deliberate tumble before undocking. At a yaw rate of 5 degrees per second, the DM is cut loose, and end over end it goes, drifting away from the Apollo.
Apollo Houston, if it'll give you a warm feeling, we're go for DM jet.
Super. We're maneuvering. Okay, she went off real good, Crip. We don't see her in the window yet. We went to hold in 15 seconds.
Yeah, everything's going super. Even down here in the motor, we're squared away. We've got our 2 roses from Cindy Diane, like she's been sending all through the Apollo program, so we're go. The weather out there at your recovery point is still super also. It's, once more, 1,800 scattered 10 miles viz, winds out of the east about 15 knots with wave heights 4 feet, may even be less. Looks like they're declining a little bit.
Apollo Control, ground elapsed time 223 hours 9 minutes, with less than 1 hour and 9 minutes to go for the burn of the SPS engine. This will bring back the command module, splash down in the Pacific northwest of Hawaii. This will be a burn of 7 seconds in duration. The command module will be oriented minus 8 degrees, pitch down. The crew of Apollo will be heads down on this burn.
Doppler data used to study Earth's ionosphere is excellent, but in the gravimetric studies, the data is disrupted by a single frequency Doppler noise that prevented the reliable identification of any so-called gravity anomalies by the experiment. Apollo initiates its retrofire burn, a 6.6 second maneuver with the SPS, the longest of the whole mission, on July 24th, 1975. The crew of 3 are headed for a splashdown point in the Pacific Ocean, 345 miles west of Hawaii.
Apollo Houston, we're all go here for your deorbit burn.
Okay, Trip, very good. So are we. The burn went off on time, according to FIDO. Good burn and good trim. Entry interface, 20 minutes and 14 seconds after retrofire.
They blow off their service module, exposing their heat shield, and barrel towards the atmosphere. Having made it successfully through entry, the Apollo begins dropping like a brick. It screams through 50,000 feet at Mach 1.7. This is where seconds absolutely matter.
The altimeter's coming off the lake.
Roger.
Mile distance is Sheppard.
Copy that.
12.37, this baby is right on. 45K.
Okay, it's all looking good here. We got data and we got you in radar contact at the ship. Okay, Apollo, you're looking super here. You're coming up on your main time and on drogue time rather, and so see you tomorrow, day after tomorrow.
It is standard procedure for the crew to arm the sequencer pyro buses below 50,000 feet and then arm the ELS, or Earth Landing System, at 30,000 feet. ELS switches in logic and auto applies sense power to barometrically activated relays that, among other things, initiate the parachute deployment sequence and inhibit the reaction control system on board the command module. But the crew makes a mistake. These two switches are not positioned in time, and the RCS command is not in the off position either. As a result, the inhibit signal was never sent, and as the valves snapped open to begin letting Earth air into the spacecraft cabin, that differential pressure sucked in powerful vapors of nitrogen tetroxide still spewing from the RCS jets. The first thing the crew notices is the fact that the forward heat shield has not jettisoned, which they do so manually. The rapid attitude change caused by the deployment of the drogue parachutes incites the RCS system to respond in kind, and for 30 seconds, powerful, toxic, caustic vapors continue to enter the spacecraft atmosphere. The crew are not wearing their pressure suits. That's been normal practice since Apollo 8. With the solenoid valves in the propellant feed system left open, CM-RCS oxidizer begins to boil and produce yet more vapors. It is estimated that the peak cabin concentration of toxic gases was some 700 parts per million. Nitrogen tetroxide reacts with air to form deadly nitrogen dioxide gas. As the onboard ECS recycles air, nitrogen tetroxide in the system reacts with water in the glycol heat exchanger, converting to nitric acid. The crew finally realizes what is going on and closes the RCS isolation valves. But, still on the descent, and having to communicate with the ground and manually operate their parachute system, they will not have a chance to don oxygen masks for 4 minutes and 40 seconds, inside one of the most excruciating environments ever survived in manned spaceflight.
Round of applause here at Mission Control Center.
Swim has a tally on the command module. Okay, pass from 600.
Tremendous round of applause here at Mission Control Center with splashdown.
Splashdown at this time. Apollo is on the water. Roger out.
Apollo splashes down at 5:18 p.m. Eastern Time, and by then, Vance Brand is effectively unconscious. Stafford and Slayton work quickly to don oxygen masks post-landing and secure themselves for recovery. All 3 astronauts have developed scar tissue on their lungs and fluid buildup. They will require a 2-week hospitalization in Hawaii. But, the troopers they are, they put on a brave face and even speak to crowds aboard the USS New Orleans less than an hour after splashdown. Apollo's final landing, a harrowing close call.
Thank you, General Hartung, Admiral Whitworth, and Ryder. The ship was right on the spot. Apollo-Soyuz, the way it's gone, I think, is a great ending to the Apollo project. It's also an example that if you work long and hard, do your planning, do your homework. In this case, it was a lot of diplomatic homework. A lot of people all together came off beautiful. And there's so many people around the world I want to thank for this. The main thing, everything went great. I know that all the people in America are glad to see this event. It was the effort of a lot of people. And the main thing is that this is the end of one era of Apollo and the beginning of another. So with that thought, I'd like to introduce a couple of great guys I've had the privilege of sharing 9 days with, besides training with for 2 years. Pete Slayton.
The ASTP mission is the punctuation mark at the end of the first space race. Just 14 years after Gagarin and Sheppard, Americans and Soviets were working together for a brief moment in space. Unfortunately, the policy of Detente was poisoned not only by the political downfall of its greatest architect, but also by the changing world of the 1970s. New, hot winds were blowing across the Middle East and Central Asia that would change the political realities once more as the balance of power shifted. It would take the end of the Cold War and a new Russia for international human spaceflight to once again become possible. And when it did, the hardware legacy of this mission would be there for inspiration. On the shelf, a little dusty, but hopefully never to be forgotten. Because when we work together, we can achieve more. crown jewels of their respective Cold War propaganda efforts. Its legacy is, look at how long is it...